Hello everyone. This video is part of a series where I go over different topics involving simple resistive circuits. This series is primarily aimed at students who are currently taking introductory physics courses. In this particular video, I'm going to discuss the concept of electrical power. The concept of power can be used in other parts of physics, but for the purposes of this video, I am going to look at how it specifically applies to simple electric circuits. We represent power with a capitalized letter P. Now the SI unit of power is the watt. It's named after James Watt. You may have noticed that most electrical devices you buy, anything from TVs, hair dryers, appliances, phones, etc., light bulbs, have a power rating in watts that is associated with them. So this is a topic that is very applicable to everyday life. The general definition of power is that it's the rate at which energy is transferred between systems or transformed into different types per unit time. So it's an amount of energy that, we measure it in joules, divided by the time it takes to transfer or transform that energy. We can write this as capital E for energy over delta T. Sometimes we don't even worry about the delta part, we just write E over T. In terms of a simple circuit, we know the battery has energy stored within itself, and then through the circuit, it delivers that energy to the resistors, and the resistors dissipate that energy. Dissipate is a funny word because it basically means to cause the energy to disappear. But, of course, energy can't be created or destroyed. It's the conservation of energy. So what really is happening is that the resistor transforms the energy into thermal energy. You can sometimes feel that when you feel the heat being given off by electrical devices such as computers or TVs, power bars, that type of thing. Just to keep things simple at this level, assume that a resistor can stand in for any electrical appliances that makes use of the electrical energy and then turns it into light or heat or motion. And so you can see here that 1 watt is equal to 1 joule per second. With electrical appliances, it is not just about the amount of energy needed, but how fast that energy can be provided. For instance, a 60-watt light bulb transforms 60 joules of energy into light and heat every second. When a battery is hooked up and needs to deliver energy to the rest of the circuit, then it does that by sending an electric current, call it capital I, that flows through the circuit. How much power the battery delivers depends not only on the battery voltage itself, but also the current that the circuit draws from it. So, how can we calculate this power? It turns out the power delivered by a battery can be calculated by multiplying the battery voltage by the current drawn from the battery. Please note that since the current that's drawn from the battery depends on the load of the circuit, the power delivered can change depending on the situation. The battery voltage is constant. For instance, you go and buy a 9-volt battery, but the current that's being drawn from it increases with the amount of circuit load. So if you're running more apps on your phone, the power need of the phone is higher and more energy is delivered from the battery per second. That is why your battery level will tend to drop off more rapidly when you're running lots of things off that battery. This formula also gives us another definition of the watt. We know that 1 watt equals 1 joule per second. But in an equivalent manner, it can also mean that 1 watt is equal to 1 volt ampere. We now move on to calculating the power used or dissipated by a resistor. When we work with resistors, the quantities we usually measure are the resistance of the resistor, we measure that in ohms, the current through the resistor, measured in amps, and the voltage drop across the resistor, measured in volts. As with the battery, we can calculate the power use of a resistor by multiplying the current I that goes through it by the voltage drop, delta V, across it. We can also write this formula in different forms due to Ohm's law, which gives us a nice relationship between voltage, delta V, current, I, and resistance, R. Ohm's law shows that delta V is equal to I times R. So if I were to plug I times R in for delta V in the power formula, I will get a new formula where you can see that power is going to equal I squared times R. Alternatively, I could have used Ohm's law of I equals delta V divided by R, plug that in for I in the original power formula, and now I would get a new formula that says power is equal to delta V squared divided by R. All of these formulas are equivalent and will give you the same result. As long as you know two of the possible values of delta V, R, or I, you can make use of this relationship to calculate the power. The law of conservation of energy is maybe the most important scientific law that we have. And it basically means energy cannot be created or destroyed. It can only be transferred or transformed. Now, in terms of electric circuits, you can state this law as the total power delivered by the battery has to be equal to the total amount of power that gets dissipated or used from all the resistors. In other words, all the energy given by the battery must be accounted for. In another video, I go through an example showing how to apply this theory and these formulas to solve a given problem. I'd like to thank you all for watching, and I hope you have a great day.